All right, this is the Atwood machine video with the forces and acceleration examples that we've been working on. For this one, I think it's a relatively easy issue again, or relatively easy problem because we only have two objects. And anytime we have, the fewer objects we have, the easier they are, except possibly the inclined plane, because then we've added a few other things with the angle, and that will be another video shortly. So here we go. Once again, we always start with labeling all of our forces. Here we have the force of gravity pulling down and the tension pulling up. And on this object, we have force of tension pulling up and once again, force of gravity pulling down. Once again, tension forces. Sorry, a little glitch in the video. Tension forces always pull away from the mass. So this tension is pulling up and this tension is also pulling up. Once again, these two are in exactly the same rope. So they have to be equal. Right? They are not necessarily equal to these forces of gravity though. Right, here we have a tension pulling up, force of gravity pulling down. These are not necessarily equal, and these are not necessarily equal. However, this tension force and this tension force do have to be equal to each other since that they are in the same rope. So, got our forces, nothing really cancels, so now it's time to start doing some math. So let's take a look. I think I'll actually start working right here so that I can use this diagram. Right, so the net force, so we have F net on M1 is going to equal, we have to kind of decide overall which way this thing might accelerate. Came across this issue after school working with someone the other day, right? We have to use the same direction for both of these. So if we're going to assume that this one is accelerating down, that will have to accelerate up. And we have to do that in terms of keeping our negative signs straight, because if we don't, we're going to get some really interesting math, which won't be correct, by the way. So if this one's accelerating down, this one's accelerating up. If this one's accelerating down, that one's accelerating up because they're attached by this rope. We can't set our equations up assuming this one is accelerating down and this one is accelerating down also, because physically that cannot happen. So we have to use our equations in terms of some sort of a physical sense. It doesn't really matter if we're correct overall in terms of our original guess, because the math will work itself out as long as we just make sure we're using the same direction of acceleration for both of these objects. So I'm going to assume, since this one has a bigger mass, this is probably the direction this one's going to accelerate, and it's probably going to make that one accelerate upward. So when I do that, I'm going to say that our acceleration is Fg minus the tension force. And then the net force on the second object then has to be the tension force minus its Fg. And maybe I should label these Fg's too, so we can kind of keep track of which one is which, because these are not going to be the same number. If I use exactly the same symbol, I might accidentally think they're the same number when I go to do the math. So I'm going to assume that yes, if the one on the left is accelerating downward, the gravity force is going to be bigger, and if the one on the right is going to accelerate up, then that tension force has to be bigger. If I set this up also as Fg minus Ft, yeah, my math would not give me any numbers that made any sense whatsoever. So I discovered that the other day and had never really made that clear, I don't think, so I wanted to make that clear when working through this problem. So as always, once we have our equations, we start filling in what we know. On M1, the net force is going to be its mass times its acceleration. Its force of gravity is its mass times 9.8 meters per second squared. And once again, I'm just going to use positive for these because I'm taking care of negatives with like these negative signs in between, which might be going up and which might be going down. So I'm just going to leave our acceleration of gravity is 9.8 for now. For the second object, 7.8 times its acceleration is going to be, and then I almost did it, it's the force tension minus the force of gravity on it, 7.8 times 9.8. Now, even though it's on here twice, right, these force of tensions are exactly the same thing. And the other thing is, again, these acceleration numbers are going to be the same. We found that out through several of these problems. If these objects are connected, they have to be accelerating at the same rate. Right? It's this tension force that is making the second one accelerate, and that tension force is the same as this one. So as this one pulls down, this one's pulling up, and it's going to be the same. And it's this one, gravity, it's pulling down on the entire thing, which makes it all accelerate. So hopefully just by logical thinking, you can understand that within this same rope, unless the rope stretches, or unless the rope gets all floppy and there's some slack in it, right? These accelerations have to be the same. And the rope can't stretch, we're assuming these are all non-stretchable ropes, so it becomes a really complicated problem. And yeah, the rope is not going to get slack in it either, so those acceleration values will be the same. So like several of we've talked about, we have two equations and two unknowns, so we have different ways of doing this. I think I'm going to solve the bottom equation for tension and then put it back up into the top equation. So then doing that, tension on the bottom one is we have the 7.8 times A, and then we move this over. The 7.8 times 9.8 is 76.4, and that's going to be added on this side. 76.44 newtons. I'm adding it on this side, and I just flip the equation around, right? So tension force is this. So then going up to our other equation, 13.7A equals, take 13.7 times 9.8. We have 134.26 minus this tension force, so it's minus 7.8A minus 76.44. Right, we're subtracting this whole quantity, which puts a negative sign in front of them. Right, it's minus force tension in this equation, so it's minus this when we do the math. So now it's just algebra. We move the 7.8A over, so we're actually adding the 7.8 to the 13.7, and we get 21.5. And then we subtract these two numbers, the 134.26 and the 76.44, and we have 57.82 dividing by the 21.5. I can kind of slide this down now that we've got a little algebra done here, and we get 2.7. And then like all of these problems, we can go back and substitute in. I can put this right in for the A in this tension formula. And I get 76.44. I get the tension is 97.4 newtons. All right. I guess the other thing that we might want to calculate is the net force on both of these blocks. Once again, we have two ways of doing that. We can just take the acceleration numbers, the 2.7 times each of the masses, and that works out fine. Or we could do these numbers again, right? This is the 134.26 from here. We could subtract the tension from that, and that would give us the net force on M1. Or we could take the tension minus this, what was it? These two numbers multiplied together was 76.44, and we could get the net force that way. Either way should work out. So I guess I would suggest maybe try it both ways and just make sure your algebra works. But the way this looks on M1, the net force, I get 37 newtons. And on M2, it should be 21 newtons, give or take. And that's the way that it works out. Once again, these two I've rounded off after our sig figs and everything, but there we go. So we have our net forces, we have the tension force, and we have the acceleration. So again, this one isn't quite as complicated in all the math. Oops, sorry, I need to give you these other answers. The algebra isn't quite as complicated since we just have the one string with the same tension in both of them, and we just have two objects. But that is the algebra for how to do an Atwood machine. Thanks for watching.